This is one of my favorite topics to teach in math. We're going to look at the Newton Quotient. So what this section is all about is it's about finding instantaneous rates of change. So first of all, what's a rate of change? You probably learned about this earlier in your math career. A rate of change is just equal to the change in y divided by the change in x. We're looking at how is y changing with respect to how is x changing. So that tells us an average rate of change between 2 points. But what if we want to find the exact rate of change, the instantaneous rate of change at 1 point? Well, what would that do to our change in x? What if change in x was 0? How do we divide by 0? And I'm going to show you the connection between this problem and how this equation here, the Newton quotient, allows us to actually solve that dividing by 0 problem. So here we go. Let's review first what is graphically an average rate of change and an instantaneous rate of change. So if I've got a function here, the function is my green function here. If I want the average rate of change between 2 points, that average rate of change would be equal to the slope of this, what we call secant line. A secant line is a line between 2 points on a curve. That would tell me the average rate of change between those 2 points, right? If I figured out the change in x and the change in y between those 2 points, the average rate of change would be change in y over change in x. But what if I wanted the instantaneous rate of change of a function at one exact point? What if I wanted to figure out how is this function changing at this one exact point? If I wanted that, I would need the slope of the tangent line. But to find the slope of a line, you need 2 points. And for this tangent line, well, what's a tangent line? It's a line that intersects a function only at 1 point. So we only know 1 point on this line. So how do we find the slope of that line? So let's look at a couple ways that we can look at how we're going to solve this problem, and how calculus is actually going to give us a great solution to this problem. So before I go there, let's look at this function here. So this function, I want the instantaneous rate of change. I want the tangent slope. So here's the tangent, and this program, so here's the tangent here to this function at that green point there. The tangent slope is 0.89. This program tells me what the tangent slope is. But how am I actually going to find that tangent slope if I only know this 1 point on the line? What we actually do, we're actually going to use secant slopes to approximate it. So I've drawn a secant between the green and red point here. Notice that secant slope is 1.39. It's not equal to the tangent slope, but it's pretty close. What happens if I move this point, what happens if I move that point closer? Let me move this back. Where was it, 0.89-ish? Tangent slope, okay. What if I move that red point closer? If I move that red point closer, notice what's happening to this secant slope. It's getting closer to 0.89. It's getting closer to matching the tangent slope. And as I move that red dot closer, closer, notice that this secant slope here, is getting closer and closer to matching the slope of the tangent. Closer. Notice these secant slopes are getting closer to 0.89. But what if I put the points right on top of each other? What happens? Oh, secant slope, error. If I was trying to calculate an average rate of change where there is no change in x between the points or change in y between the points, I would be doing 0 divided by 0, which is called indeterminate form, and it's an error. So what we're going to be looking at, we're going to look at what are these secant slopes approaching. As I move the point closer, the secant slopes seem to be approaching the slope of the tangent. And what if I move the point to the other side and then approach it closer and closer to the point on the tangent? The secant slopes get it closer and closer to matching the slope of the tangent. All right, so let's look at a specific function now. And we're going to go through and use the Newton quotient for this function to actually figure out the equation of what we'll call the derivative. But before we do that, I'm going to show you in Desmos this function. So this function is a quarter x squared minus x plus 1. That's our red function here. And I've got Desmos to draw the tangent slope for us. But let's look at how we can use the secant slopes to estimate the slope of the tangent. So once again, I've got the purple line is the tangent slope. The green line is a secant slope. And if I move this point here, this green point here, if I move it closer and closer to the actual point of the tangent, so I make the secant smaller and smaller and smaller, you'll notice that the slope of the secant is changing. And what we discovered before is the slope of the secant should be getting closer to the slope of the tangent. Now, I haven't shown you anywhere what the slope of the tangent is. I mean, we could figure it out graphically. But notice, right now, the slope of the secant is 1.64. And as I move this point closer, the slope of the secant is getting closer and closer and closer and closer. It looks like to 1. Like right now, where the points are barely apart, the secant slope is 1.025. If I put them right on top of each other, once again, so let me set this difference, we call that difference in x values h. Let me set that h value to 0, so they're right on top of each other. Notice the secant slope once again is undefined. It would be 0 over 0. So as I move the point closer from the left, once again, the secant slope right now is 0.5. As I move it closer from the left, it's now at 0.775. Closer and closer and closer and closer, it looks like it's approaching a value of 1. So what I've just shown you here is we're actually looking at the limit of these secant slopes. We're looking at what are they approaching as the points get closer and closer and closer together, as the change in x values are getting closer and closer and closer to 0. So let me kind of write down what we've just kind of discovered. So if I want to calculate the instantaneous rate of change, what I want to do is I want to make the difference in x values as small as possible. The smaller the difference in x values of the points on the function, the closer the secant slope gets to matching the tangent slope. And if we could, so the idea is if we could make the difference in x values 0, we would have the instantaneous rate of change. But remember, if we want the slope of the secant, I do change in y over change in x. So if my change in x is 0, my change in y would also be 0. How do we do 0 divided by 0? How do we do this problem? How do we divide by 0? That's the main problem of calculus. So let's see if we can figure out how we divide by 0. What we're going to do, we're going to look at, so I've made up a function here. If we want the slope of this tangent, what we're going to do is we are going to make a secant slope that we think approximates it. So I'm just going to draw a secant here. So my secant is between these 2 points. Now, the slope of this secant is not equivalent to the slope of the tangent. It's pretty close. And I can summarize the points here on my function. So let's say this point right here is some point x f at x, right? F at x is just function notation for the y value for a given value of x. So that's point x f at x. Now, if I move a certain number of units to the right and then up, well, this amount of units I've moved to the right, that's my change in my x values. And I'm just going to call that h. So the change in x values is h. If that's true, then this point up here, this red point here, is point x plus whatever h units I've moved to the right is, x plus h, comma, and then f at whatever x plus h is. That's that point. So I've got 2 points. I want the secant slope. I want the average rate of change between this point, the blue one, and the red one. If I can find that, and if I can make h, if I can make this change in x values as small as possible, if I can do that, I'll get a good estimation for the instantaneous rate of change. And if I could find a way to make this h 0 and still be able to do the division, then I would have the exact instantaneous rate of change. So what we're going to look at doing, we're going to look at finding the limit. So I'm going to write what the Newton quotient is. So keep on, don't forget rate of change. Don't forget rate of change. It's just change in y over change in x. That's all we're going to be doing. We're going to be looking at how the y values are changing divided by how are the x values changing. But we're going to be looking at what is it approaching as we make this h value, this change in the x values, as small as possible. We want to see what's happening as that gets closer and closer to 0. So here's the notation for how we write it. If we want, the Newton quotient tells us that if we want the instantaneous rate of change of y with respect to x, this means instantaneous rate of change of y with respect to x, it can be written like this as well, f prime at x, it's equal to the limit as h gets closer to 0 of, we find the slope of this secant where we make h get closer and closer to 0. So if I want the slope of this secant, I would do change in y. So here's my y values, here and here. So do f at x plus h minus f at x, those are my y values, divided by the change in my x values, x plus h minus x. x plus h minus x. Well, x minus x is 0, so my denominator is really just h, right? H tells us the change in x values. So here we go. Well, we can't just put 0 in for h because then we're dividing by 0, and the numerator would become 0 as well. That's called indeterminate form. We don't want that, but we're going to do some algebra, and we're actually going to do something called remove the discontinuity, and then be able to figure out what the slope of the secant is approaching as h gets closer and closer and closer to 0. So here's how the formula actually works. Hopefully you have a decent understanding of where the formula comes from. It's just the slope formula. It's just change in y over change in x. But we're looking at how does the slope of this secant, what does the slope of the secant get close to as we make this change in x, this h value, get closer and closer and closer to 0. Right? And when we do that, let me remind you about the Desmos. As I make the h value, which is change in x, as I make that get closer and closer and closer to 0, the slope of the secant, the green line, gets closer to matching the slope of the tangent, the purple line. So here we go. Let's use the Newton quotient. So let's find, so that function I showed you, the red one in Desmos, let's find the equation for the instantaneous rate of change of this function, and then we'll use it to find the instantaneous rate of change when x is 4. So if we use Newton quotient, we start by writing f prime at x equals, and we'll have to write limit as h approaches 0 of f at x plus h. Well, here's f at x, right? This is f at x here. If we want f at x plus some h value, just change all the x's to x plus h. So it would be a quarter x plus h squared minus x plus h plus 1. This is my f at x plus h function. And then I need to subtract f at x, which is just this function. So subtract a quarter x squared minus x plus 1. And this all goes over h. And what we're going to do, we're going to expand out the numerator, collect our like terms, and hopefully be able to remove this discontinuity that we have here. Right? If I plugged in 0 for h right now, this would be an undefined function. But we're going to expand it out and see what happens. So hopefully you're good at your arithmetic skills here. So I'm going to keep writing limit as h approaches 0. X plus h squared, make sure you know that means x plus h times x plus h. You have to FOIL it out, and you get x squared plus 2xh plus h squared. And then minus x plus h, so minus x minus h plus 1 minus a quarter x squared plus x minus 1, right? Distribute the minus to everything. Okay, let's keep going. Oh, and this is all over h. Keep going. Limit as h approaches 0. I can distribute my quarter in now, so a quarter x squared. A quarter times 2 is a half, so plus a half xh plus a quarter h squared minus x minus h plus 1 minus a quarter x squared plus x minus 1 all over h. Okay, it's fully expanded now. Let's start doing some collecting and see what we have. So it should collect fairly nicely. And after we see what happens, I'll explain to you what we can expect to happen every time we use Newton quotient. So I've got a quarter x squared minus a quarter x squared. Those cancel out with each other. I've got a negative x plus x. Those cancel out. And I've got a 1 minus 1. Those cancel out. So what's left? Look at every term we have left. And notice what's in common with all of the terms that are left. Right? I have a half xh, plus a quarter h squared minus h. What's in common with all three of those terms? Notice they all have an h. I can common factor out that h. Oh, I forgot to write limit with these ones. Sorry, I still have to keep writing limit here until I can actually plug in my 0 for h. And I can't plug it in yet because what I have there is an h in the denominator. And if I plug in 0 for h, I'm going to get 0 over 0, which is still indeterminate form. So I still have to write limit equals limit as h goes to 0. Same thing here, equals limit as h goes to 0. And I can common factor out an h, a half x plus a quarter h minus 1 all over h. And then something wonderful happens here. We can get rid of the h in the denominator. This is called removing the discontinuity. So there is no more h in the denominator. What do I have left? I have the limit as h goes to 0 of a half x plus a quarter h minus 1. Now I can actually plug 0 in and get an answer. I couldn't plug it in before, right? If I plugged it in before, I would be dividing by 0. And it would make the numerator 0 as well. I'd have 0 over 0, which is undefined. It's indeterminate form. So actually now we can plug in the h and get an answer. So we can stop writing limit. So it equals a half x plus a quarter, and now replace the h with the 0, minus 1. So this equals a half x minus 1. This is the equation for the instantaneous rate of change of the function. So f prime of x equals a half x minus 1. This would tell us the slope of the tangent at any point x on our original function. So if I wanted to figure out the slope of the tangent when x is 4, right? Remember back to on Desmos, we were looking for the instantaneous rate of change at an x value of 4, right? This purple point here is at an x value of 4. I want the slope of the tangent when x is 4. What I can do now is just use this equation I found that tells me the instantaneous rate of change, right? The slope of the tangent at any point I want. So I can find f prime at 4, just by plugging in 4 for x into this equation. So f prime at 4 equals a half times 4 minus 1. Half of 4 is 2, so 2 minus 1, which is 1. So f prime at 4 is 1. What does that mean? It means the slope of the tangent on a point that has an x value of 4 on the original function, the slope of the tangent is 1. And look at the slope of this purple line, right? Just do rise over run. For this purple line, between this point and this point, we rise 1 and run 1. So the slope, just like we found here, is 1. The instantaneous rate of change, the slope of the tangent, is 1. Let's work at trying another Newton quotient question. Let's find the equation of the derivative of this function, x squared minus 5x plus 4. So just a reminder of the equation of the derivative of a function, right? Derivative is just another word for an equation that finds us the instantaneous rate of change of a function, equals the limit as h goes to 0, so as the change in x is getting closer and closer to 0, so as the secant line is getting smaller and smaller and smaller, of change in y, so f at x plus h minus f at x, over our change in x, which is just whatever this h value is, however far we moved over from the original point. And then we can actually plug in our function. So for f at x, we just plug in the actual function. We can just plug this in for f at x. That's what f at x is. But to plug in for f at x plus h, we replace each of these x's with x plus h. So here it is. Limit as h goes to 0 of f at x plus h. So change each of the x's to x plus h, and it gives me x plus h squared minus 5 times x plus h plus 4, and then subtract f at x, so subtract this function, subtract x squared minus 5x plus 4, and this is all over h. And remember, I'm finding the limit, I'm finding what this is approaching. I'm not actually plugging in 0 for h yet because this would give me indeterminate form. So I'm going to do all my expanding and collecting and hopefully get rid of the discontinuity. So x plus h squared is x squared plus 2xh plus h squared. Distribute the negative 5, minus 5x minus 5h, plus 4, and then subtract f at x. So subtract x squared, subtract negative 5x, which is plus 5x, and subtract 4. Now that it's fully expanded, once again, look at what cancels. Everything that doesn't have an h should cancel. X squared minus x squared is 0. Negative 5x plus 5x is 0. And 4 minus 4 is 0. The only terms that are left all have an h. 2xh plus h squared minus 5h. They all have an h. So I can common factor out an h, and then I can remove the discontinuity and figure out what the tangent slope would be for any value of x that I want. So I'll common factor out the h, 2x plus h minus 5. And now I remove the discontinuity. H divided by h is 1. I can cancel them out. all I'm left with is 2x plus h minus 5. So I can now actually sub in 0 for h and get an answer. So we don't have to write limit anymore. We can actually sub in 0 for h, 2x plus 0 minus 5. And I get the equation of the derivative f prime of x equals 2x minus 5. So I can find the slope of the tangent at any point on the function that I want. If I wanted to evaluate the slope of the tangent when x is 1, I would just do f prime at 1, and I would figure out that the slope of the tangent is negative 3. All right, that's it for Newton Quotient. Hope you enjoyed. Leave a comment, subscribe, make sure you like the video.